Okay, any questions before we start? Now, you see, in this example, what we are actually doing is, also remember, the V is equal to I times R. Now, this V is nothing but the potential difference between the two ends. So, if you open your legs, if the distance between your 2 feet are further away, the current is the same. You are increasing the resistance, so the potential difference between your feet increases. Other questions? Okay, so your friend's question is this one. We have this conducting sphere. Now we have already discussed that inside the electric field will be 0. Since inside the electric field is 0, the potential difference between any 2 points inside the sphere will be also 0. But if you take a point at infinity, if you set the potential at that point to be 0, then you can calculate the potential difference, let's say, at this point P, the potential difference between the point P and the point at infinity will be minus E dot del from infinity to P. But remember, here the electric field is not 0. Since the electric field in this region, out of this sphere, the sphere is, let's say, positively charged. There is an electric field in this region. You are creating a potential difference between infinity and inside your sphere. Now the question is, which point has 0 potential? Well, it's up to you to choose. I mean, you can choose any point to have 0 potential. The only thing we can calculate without any ambiguity are the potential differences. So inside we know the potential difference is 0. And we know that the potential difference between this point and the point at infinity is non-zero. So if you set the potential inside your sphere to be 0, you can choose that. You can say that the potential inside is 0. In that case, the potential at infinity cannot be 0 because the difference is not 0. So you can either set the potential at infinity to be 0 or the potential at the inside your sphere to be 0. Both are valid choices. Conventional choice is to set the potential at infinity to be 0. Other questions? I mean, if you have 2 unconnected capacitors, you have 2 unconnected capacitors. I mean, you have to be told how the capacitors are connected. Or you have to decide how you want to connect your capacitors. Do you want to obtain a larger capacitance or a smaller capacitance? Other questions? Mm-hmm. No. I mean, it is a choice. You don't know. I mean, you can choose it to be non-zero. No, you see, the only thing we can calculate are potential differences. Now, potential differences doesn't tell you the value of the potential at anywhere. So you can just choose one arbitrarily. So you cannot prove that the potential at infinity is 0. It need not be. You can just define it. The only thing you can measure, The only thing you can calculate are the potential differences. So usually it is chosen to have potential equal to 0 at infinity. It is a choice. You can choose a different convention. It's up to you. Mm-hmm. Well, that's if you have a dielectric that satisfies this relation, the electric field inside the dielectric is equal to the electric field applied divided by your dielectric constant. Now, in this case, this is the same everywhere. This will be the same as, you see, applied electric field is always proportional to 1 over epsilon 0. And if you divide it by k, this will be proportional to 1 over k epsilon 0, always. K will not appear anywhere else in this proportionality constant. Epsilon 0 will not appear anywhere else in this proportionality constant. So this is the same thing as 1 over epsilon. So in the presence of a dielectric, of course, assuming that everywhere is covered with a dielectric, or you are only looking at the region where you have a dielectric, in that region, you can just replace epsilon 0 by epsilon, and you do take into account the properties of the dielectric, assuming the dielectric satisfies this relation. Not all dielectrics satisfy this one. Most of them do, but not all of them. Outside the sphere, okay, you see, we have, now let's look at this sphere. It is uniform. Let's say it's a sphere of radius r that carries a total charge q. It is uniform. Okay, so what can you say about the electric field? It's a spherical shell. First of all, the electric field, well, we want to use the Gauss law. What kind of a surface should we choose? A sphere, why? Well, how do we know the symmetry? How do you use the symmetry? Well, the electric field, we know that it can only depend on the radial distance from the center. And it is in the radial direction. Now, r is distance from the center of the sphere. It's not an arbitrary distance. You cannot just define r to be the distance from, I don't know, somewhere, some point on the shell. It is the distance from the center of the sphere. That is what we call the r. And this r hat vector is a unit vector away from the center of the sphere. The point is, we already have chosen a special point. Now let's consider two Gauss surfaces. One is inside the shell of radius r. Now we know that all the points on this Gauss surface are at the same distance from the center of the sphere. So this is a constant for this Gauss surface. That constant we can just take out of the integral. E dot ds around this Gauss surface is, we know that the electric field is in the radial direction. ds is also in the radial direction. This is equal to ER times ds. Now ER is just a constant which I can take out of the integral. The remaining part is nothing but the sum of the areas of the patches that make my sphere. That gives me the total area, 4 pi r squared. This should be equal to, by Gauss law, the total charge inside my sphere, which is Zero. I have a spherical shell. No, it's a shell. Inside is empty. Now let's choose another Gauss sphere, this time outside the sphere. This is my second sphere. Again, let's call the distance, this time maybe r prime. Some sphere out of my shell. The calculation of this Gauss integral will be the same. It will be E times r prime, 4 pi r prime squared. It's just the same result. I mean, here we only use this fact and the fact that we are integrating over a sphere. We didn't really use anything that whether this sphere was inside or out of the shell up to this point. Now, what is the charge inside? Q. So this should be equal to Q over epsilon 0. So E of r prime is equal to 1 over 4 pi epsilon 0 Q over r prime squared. So now we know that, yes? Now, now let's finish this one first, and then let's discuss your question. Okay, let's finish this one. So we know that the electric field is always in the radial direction in this problem. What we do, and we have found what this constant is inside for a point inside the shell and for a point outside the shell. Now we can just combine it. The electric field at an arbitrary point is equal to, it is in the radial direction, 1.4 pi epsilon 0, well, let me remove it. And it is 0 if we are inside the shell, and it is 1 over 4 pi epsilon 0 Q over r squared if we are out of the shell. So if you look at this expression, out of the shell, it is nothing but the electric field of a point charge. If you are an outside observer, you will not distinguish a spherical shell from a point charge if you are outside the shell. Inside, of course, it behaves completely differently. It's not a point charge. But out of the shell, the electric field created by a shell and the point charge, they are identical, as long as you identify this r as the distance from your point charge. So the inequality of the electric fields of a spherical shell and the point charge is only if you are out of the shell. In that case, the electric field created by the shell is the same thing as the electric field created by a point charge at the center of the shell. Again, this equality is valid only if you are outside the shell. Definitely not inside. Now let's come back to your question. You are asking, what if we have another point charge inside the shell? Okay. Okay. True. Why not? I mean, so your friend is asking this question. We have this shell. This time it is neutral. We put a point charge at the center of this shell. Now, in this case, the shell has absolutely no effect whatsoever. Now we can do the same treatment. So we can do the same treatment whether we are inside the shell. Q enclosed will always be Q. So the electric field in this case will always be whether we are inside or outside. It will be in the radial direction, 1 over 4 pi epsilon 0 Q over R squared. So what is puzzling you? Okay, let's do another problem, not this infinitely thin shell, but let's discuss what happens if we have a thick shell, thick conducting shell. This is our shell, conducting. Inside we put some positive Q charge. So what is the charge inside my conducting shell? It will be minus charges. What is the total charge in the inner surface of the shell? Minus. So we have the charges here will be negative. The total charge will again be minus Q. What about the charge on the outer surface? It will be plus. The total charge on the outer surface? Positive. Well, since the area is a bit larger, the density will be smaller, but so that the total charge will still be plus Q. Now, if we want to find the electric field over here, inside. Now, this electric field will be the electric field created by the charge Q, plus the electric field created by the minus charges, plus the electric field created by the positive charge. No, the answer is not that. What is the electric field created by the negative charges? At this point, P. It is 0. The negative charges in the inner surface do not create any electric field inside. No, I mean, as long as you have a spherical shell, the charges on the spherical shell never create an electric field inside. Why? You can also think of it like this. We have these minus charges. Let's just look at the minus charges. If we want to calculate E minus at this point, well, let's just take some patch over here. The electric field created by these minus charges, in which direction they will point to? To the left. So these will create an electric field in this direction, but I also have all the electric negative charges on the other side. And these charges will create an electric field right in the opposite direction, and they will cancel. So if you are inside the shell, all the charges on the shell, their contribution to the electric field, they just cancel each other. That's why E minus inside the shell is 0. Similarly, E plus. The E plus inside the shell in this problem is 0. So these two contributions are 0 inside this shell. Now let's look at this point. Now let me call this E1. Let's calculate the electric field here. Again, the electric field at that point, I can decompose it in terms of the electric field created by the Q charge, the electric field created by the negative charges, plus the electric field created by the positive charges at that point. What is the electric field created by the positive charges at that point? 0, because we are still inside the shell which holds the positive charges. So this is 0. And E2 minus the electric field created by the negative charges at this point will be equal to the electric field created by the Q charge with a minus sign, but in the opposite direction. So that the total electric field inside the conductor will be 0. Sure. I'm implicitly using the Gauss law. I already know that inside the conductor, at least in electrostatics, the electric field should be 0. From the Gauss law, I know that the positive charges do not create an electric field inside. This is 0, so the remaining two should cancel each other. Okay. Well, you see, when we are saying that if you are inside the shell, the electric field created by the charges uniformly distributed on the surface of the shell do not create an electric field, we are not saying anything about the size of this shell. And we are not talking about at which point you are. So independent of which point you are inside the shell, independent of the size of the shell, the electric field inside a spherical shell is always 0. Whether it's small or it's large, whether you are looking at a point close to the shell or whether you are just at the center, it doesn't make any difference. It is always 0. So this is the question. We have an insulator, or let's call it a dielectric. And we have some positive charge sitting over here. What will be the electric field at the center? It has a complicated expression. Is this your question or you're asking? This is the question. So there's a dielectric. Outside the dielectric, we have some positive charges. Don't worry, you will solve this problem in your 3rd year. And the only thing we can say at this point is that the electric field in the dielectric will be much less than the electric field that would be at that point if there was no dielectric. But the precise value, you can solve for it, but wait a bit. Okay, so this is your question, if I understood it correctly. We have a conducting shell. And outside, okay. Oh, okay, so you have a conducting shell, uniform, and it has a total charge Q. How will it be distributed? Any answers? It will be on the surface. If you have a conductor, the charges will always go to the surface. Inside, you cannot have any charge. In electrostatics. Because we already know that in electrostatics, the electric field inside should be 0. If the electric field inside is everywhere 0, just imagine a Gauss sphere, Gauss surface inside the conductor, E dot ds is always 0. So whatever surface you can imagine, as long as it always lies inside the conductor, the enclosed charge should be 0. So that already tells us that we cannot have any charge inside. if there is any charge, if the conductor has a net charge, the charge has to be on the surface. If there is a plus Q charge, the positive charge will be on the surface. If you put some another charge inside, then it will also induce charges in the inner surface of the conductor. But nevertheless, it is still on the surface. You will have some negative charges on the inner side. You never have a charge in the inside of a conductor. So the electric field lines will go until the surface, terminate there on the negative charges, and then we will have new electric field lines on the outer surface. This is how they will look like. Inside the conductor, there will be no electric field lines. Sure. You see, again, by Gauss Law, if you put any charge inside, the charge induced in the inner surface of the shell should always be negative the charge you put over here. So the remaining charge should go out to conserve the total charge. On what? Right on the surface. Okay. Well, you see, the surface only exists in the mathematical sense. It doesn't really exist in physics. So, the question, okay, it can be relevant for the mathematics, and usually to be consistent, one just takes half of the charges, just for consistency in certain calculations. But in reality, you don't have this surface. You always get some charge distribution close to the surface. There's no mathematical boundaries in physical systems also. There's always a transition. Well, just divide the charges in two and whatever you get. You see, now what we are saying usually is, okay, so here E is equal to 0. This is a conductor. Here E will be non-zero. Now, we don't have this very sharp transition. This is the magnitude of the electric field as a function of the position. Here we are saying that we have this surface and this is 0. Now, this doesn't exist. In reality, if you just enlarge this region, what you would get is mainly you have a constant electric field, and at a very short distance, it smoothly goes to 0. This is a very short distance. Now, mathematical surface you obtain when you just set this width to be 0, but it's not 0. Now, when you are saying, what happens if I put my Gauss surface right at the surface, I would ask you, are you putting at this point or at this point? Well, usually, if you still would like to stick to the concept of a mathematical surface a Gauss surface right at this surface between two physical regions, usually you just choose it in the middle. But as I said, it's not a useful concept. In which question, for example? Well, You see, the questions are usually phrased with a bit of attention. You will be most of the time asked about the electric field right out of the surface or just inside the surface. You will never be asked about the electric field at the surface. If I am careful while preparing the question, I always add those things. If I ask such questions, it mainly means that I'm careless. Almost always you will get this classification whether you are looking just inside the surface or just outside the surface. Well, I'm not asking any questions, you are asking. No. Let's phrase it properly. What we did was when we assumed the point charge, we assume that the potential of when there's only a point charge, we assume that at infinity the potential is 0. Yes. Sure. For a point charge, we can set the potential at infinity to be 0, whether it is a positive charge or a negative charge. It doesn't make any difference. Mm-hmm. Yeah, you see, when we were defining the potential at the point of the point charge is infinite. If you want to bring a test charge from infinity right at top of a point charge, the work that you have to do is infinite. That's why point charges cannot touch each other in the physical solid sense of the word. Now, if they are one is minus, one is plus, they will still not touch each other because of other reasons. Mm-hmm. So you're saying that we have positive charges here, negative charges here, positive charges here, negative charges here. Now the question is, why don't these positive charges move to this plate? Well, you can just think of this process as induction. When you have a metal, a conductor, and you bring some positive charge close to it, what it will do is it will just attract the negative charges. Now, hold on. Now you have it will attract the negative charges, and what remains will be positive. Now between these positive and negative regions, you have all this conductor, not just a thin wire. So this thing and this question is the same thing. So if you put positive charges over here, they will attract negative charges. Where is the electric field here? In between the plates. And then you have an electric field in between these plates. No. Okay, add the fringe effect. Yes. So this is your question. So we take two capacitors, then we charge them. Right, so this is positive, this is negative, this is positive, this is negative. This is capacitor A, capacitor B. And then what we do is we just take these plates. So this is capacitor A, plus and minus. Then you take the other capacitor. This is minus, this is plus, and reverse it and connect it like this. So what should happen? Nothing. What do you mean? Nothing should happen. Aren't they in equilibrium now? Nothing changes. And we have negative charges over here, negative charges over here. So all this conductor has a net negative charge. Nothing. I mean, well, usually you don't do these tricks. I mean, what's the point in doing these tricks anyway? And usually what you do is you just connect the capacitors to a battery and then see what happens. Okay. Again, we have the same system. We connect them to a battery. A, B, positive, negative, positive, negative. So we bring them here. This is A, positive, negative. This is B, negative, positive. Okay. Uncharged. Okay, so what will happen? What will happen? So let's say, what is the charge, initial charge? This is V. What is the initial charge of A? C times V. In this configuration, the final, what is the charge of A and the charge of B? By the way, if there is anybody who wants to give the homework, this is your last chance. From now on, I will not accept homeworks after 10 minutes. So what will happen now? Okay. So how do we use the charge conservation? Charge should be conserved. Okay, that is given. How do we use charge conservation? Why the average? Okay. Your friends are basically saying the same thing. So the charges will be, of course, they redistribute itself because initially the charges, the potential difference between these 2 points is 0. There's no charge in this capacitor initially, right at the moment that we connect it. So there's no potential difference between these 2 points. But when you look at the potential difference between these 2 points, right at the moment that we connect them is V. Now, that cannot be in electrostatics, because since these 2 points are connected by a conductor and these 2 are connected by a conductor, the potential difference across this capacitor and the potential difference across the other capacitor have to be equal when equal electrostatics is reached. So what do we know? Okay, again, from this relation, the potential difference across a capacitor is nothing but the charge over the capacitance. So this is Ca. So let's look at this one. Okay, first of all, we know the charge should be conserved. So Q1 plus Q2 has to be equal to Ca times V. This is the initial charge of the A capacitor. The B capacitor is empty. This is the total charge after they are connected. Furthermore, we know that the VA should be equal to VB. The potential difference across the A capacitor should be equal to the potential difference across the B capacitor. But this tells me that Q1 over Ca should be equal, let's say, Qa, Qb. Qa over Ca should be equal to Qb over Cb. So we have two equations for Qa, Qb, this one, and two unknowns. So you can just solve it. The rest is algebra. So effectively, the charges will flow in this case until the potentials across the capacitors are equal. I mean, you see, when you want to talk about some parallel connection or series connection, again, you imagine a complete circuit, not just one element and two elements connected. And you imagine sending some current. Do the two capacitors, is it the same current that passes through the capacitors? Or is it different currents that is passing through the capacitors? So that is mainly what distinguishes whether they are series or parallel. This is not a circuit. This is not a circuit in which you have a battery which creates a current. So it doesn't make sense to classify it anyway. Now, series connection just means that it is the same current that passes through your elements. That is what means the series connection. So first of all, you have to have something that creates a current, and you have to be able to determine where the current goes. So if two elements carry the same current, then they are connected in series. So for example, if you have a battery, this is what creates the current. And then you have, let's say, a capacitor and a resistor. If a current arrives, then when they reach here, it will split into two. So now a different current passes through the resistor and the capacitor. So we say that they are in parallel. Now, if you have the same battery, you have a capacitor here and a resistor here. This current I just goes across the capacitor and also across the resistor. So they are connected in series. You can imagine a third circuit, let's say. Okay, there is I. This is I1. This is I2. Here still I. Okay, it doesn't really make too much sense to say that this resistor and this capacitor are connected in series. They are not. They are neither connected in parallel. But these two resistors, they are connected in parallel. Furthermore, this combined system, not just one resistor, but this combined system is connected in series with the other capacitor. So do you agree? Now this is the question. So we have the initial capacitor charged by some, let's say, Q1, Qa. This is your capacitor A. Then you connect it to the second capacitor, just like in the previous problem. Then this is, let's say, Q1 and Q2. Here you have some energy, total energy stored in your capacitor EA. Here you have E1 and E2. So EA, is it equal to E1 plus E2? It should be But does it turn out to be when you calculate it? And what happens if they are not? Okay, on one hand, as your friend points out, we know that energy should be conserved. So we have some energy here. If it is distributed into capacitors, the energy afterwards should be the same as the initial energy from one side. But on the other hand, when you actually do this calculation, you calculate the charges after they are connected, calculate the energy stored in each one of the capacitors, and try to find whether they have, you find the E1 and E2, you sum them up, compare it with EA, they turn out to be not equal. So how does the distance resolve this problem? Okay. So if you want to answer this one, you have to tell me also a way to calculate this difference. Which means, how can I calculate it? Okay, this is how we calculate these ones. So where did it go? We are talking about electrostatics. We are say that we reached electrostatics and we compare these two cases, energies. Not really. Okay, this is something that we will be discussing next week after the exam. What happens to the difference? Okay, now it's time for a break. Just go for a 10-minute break. We will continue after the break.